Welcome to day 7 of our learning series. Today's topic is one of the pillar of programming functions. By the end of this session, we will understand what functions are, how to declare and define them, pass data through parameters, return values, and apply recursion. Why are functions so important? Image building a house with no room, just one large space. Miss Right. Functions let you divided your code into neat manageable rooms, each with a specific purpose. This make your programs reusable, clean and easier to debug. Let's remark on this journey of mastering functions, the foundation of modular code. What is a function? Let's define it simply. A function is a reusable block of code that performs a specific task. Think of it as a mission. You give it input, it processes it, and gives output. Why does this matter? Without functions, we did have to repeat the same logic over and over again. Imagine writing the same 10 lines of code every time we want to print a message to calculate tax existing right. In Python, print is a function, so is length, range, and many others. Reusable, modular, maintainable. Later, we will learn how to build our own. For now, just appreciate their role in keeping code dry. Don't repeat yourself. Why use functions? So, why go through the effect of learning and using functions? Here are four key reasons. Code reuse. Write once, use multiple times. Easier debugging. When a bug appears, you only need to check a small functions. Better organization. Functions group logic by purpose. Improved readability. Well named functions like calculate salary are self-explanatory. Let's reflect in your project. Where could you have used a function instead of repeating code? Talk to your neighbor or note down an example. Discuss it briefly. The goal is to internalize that every repetitive pattern can be turned into a function. Function declaration versus definition. In language like C, functions are often declared before they are defined. Declaration means promise to the compiler. Definition means actual code block. Here an analogy. Declaration is like booking a table. You are telling the restaurant to expect you. Definition is when you actually show up and eat. Python merges both into one. But in C, this distinction improves code organization and allow cross-file function usage. Real-world analysis. Declaration. Function declaration example. Let's look at a full working example in C. We first declare the function int add int a int b. Then we define it later in the program. Int add int a int b, return a plus b. Int main, we call it int result equal to add number 1 number 2. Why separate declaration and definition? It helps when working in teams or large files. We can declare functions in header files and define them elsewhere. Think, think about organizing your code across multiple files. This structure makes collaboration easier. Function declaration and definition in Python. Let's switch gears to Python. It simplifies the function creation by combining declaration and definition in one go. Example: def add ab return a plus b. Unlike C, we don't specify data types or return types explicitly. This makes Python code cleaner but also places responsibilities on the programmer to ensure the correct input types and returns. Note: Python function must be defined before they are called. Python uses indentation to mark code block instead of curly braces. Quick audience quiz. What would happen if you define add AB but try calling it before its definition in the same script? Calling a function. Now that we have defined the function, how do we use them? We call a function using its name followed by parenthesis and we provide any necessary argument. Example, into result equal to add 5, comma 10 or in a Python print add 3, comma 4. When you call a function, the program jumps to the function, executes the code inside, then comes back with the result. Think of it like ordering food at a restaurant. You place the order, call the function, the chef prepare it, execute the body, you receive the meal, return value. Parameters called by value. Now we shift to the concept of how parameters are passed into a function and that is important. Call by value is the default in C. This means a copy of the variable is sent to the function. Change inside the function don't affect the original variable. Example, void change value index, open the bracket, x equal to 20, close the bracket. Calling this function with a number equals to 10. Why not change number? Why? Because only a copy is altered. Analogy, image giving us someone a photocopy of your notes. They can scrub on it all they want to, your original stays on the same. Call by value example. Here contrast example. Void increment int a x equals to x plus 1 and close the bracket. In main function int a equals to 5 increment a print of percentage d and a. Output is 5. Why does it still print 5 even though we incremented it inside the function? Because x is just a copy of a. Once the function ends, x disappears. It never changes the original. Call by value protect the original data. It's a safe but limits modification unless we return a value or use point. Call by reference. Now let's contrast that we call by reference. Instead of passing a copy, we pass the addresses of the variable. So the function works on the original data. C allows this using pointers. Example, white swap int a into b, open the bracket, int temp equals to a equals to b equals to temp and close the bracket. This swap function actually works because it modifies the value stored at the memory addresses of x and y. Int main swap x and y we use to send the address. This is extremely useful when working with large data structures when avoid copying large amount of memory. Function return values. Functions don't just do things, they can also return values. When a function completes its task, it can send a result back to the caller using the return statement. Consider this in everyday terms. You ask someone to calculate your bill. They go do the maths and return the total. In programming, in add int a int b and open the bracket, return a plus b and close the bracket. In this case, add return an integer. That value can be stored and printed and used in further calculation. The data type of the return value must match the function declare return type. A function can return only one value. If your function returns nothing, its type should be void. Return values example. This slide revisits our classic example. This is simple and powerful. The result of add 5, 10 is returned and stored in result. The use of return values lets functions send information back to whenever they were called. Without this, we did need global variables which are often bad practice. Think about other operations. Returning a Boolean result, returning a float like an average, returning a character from a grading function. Functions. Not all functions return value. Some simply do something. These are called void functions, meaning they don't return anything. Think of them like comments. They perform tasks like printing output, logging data, and modifying external variables. Example in C. Since create return nothing, its a return type is void inside main, we just call greet and it's a print the message. A void function can still use return to exit earlier without returning a value. Question. Why use void instead of just returning 0 or no? Answer. Cinematics. It's clearly to indicate when a function is used only for side effects. Void function example. This code illustrates a full example. This function does exactly one thing. It prints a greeting. This is a great pattern for logging messages, printing reports, displaying error notification. Use void functions when you don't need a return value. Challenge. Write a void function name thank user that prints thank you for using our app. Now try modifying it to include the username using a parameter. This simple exercise reinforces the importance of understanding return types and function design. Recursion. What is it? Now we enter on one of the most intriguing area of functions, recursion. Simply put, recursion is when a function calls itself to solve a smaller version of a problem. Think of recursion like a set of a Russian nesting dots. You open one and inside it is a smaller version of the same thing that continues until you reach like a smallest one, the base case. Elements of a recursion. The function calls itself. There is a base case that stops the recursion. Each recursive call handles the smaller subproblems, factorials, tree traversal, file system navigation. Let's take an everyday example. If you are standing in a line and ask the person in front of you, how many people are ahead of you? And they ask the person ahead of them, and so on. That is recursion. Base case and recursive case. Let's dive deeper into the two pillar of recursion. This base case is what stops the recursive calls. The recursive case is what keeps the function going by calling itself. Example is a factorial. It calls factorial which call factorial 1, which call factorial 0. Then start returning 1 into 1, 2 into 1, 3 into 2 equals to 6. Each step is stored in memory until the base case is reached. Visual learners draw this a stack of function calls and they show how the result from the bottom up. Factorial concept. To understand recursion better, let's first review what a factorial is. The factorial of a number n written as n is n into n minus 1 into n minus 2 and 2 and so on 2 into 1. Example 5 factorial, 3 factorial, 0 factorial. Real world uses permutation and combination in maths, calculating possible arrangements appears in algorithm and dynamic programming. Pause for a moment and ask, why is 0 factorial and 1? It may seem only odd, but it makes the maths consistent in combinators. Is exactly one way to arrange 0 items. Factorial in code. Let's now bring all that together in a code. This code is elegant, short, clear, and powerful. But B. Cartesian. Without the base case, if n equals to 0, the function would cursive infinitely and crashes. Common debugging tip. Add print statement to trace recursive code. Modify this function to handle negative inputs by retrieving -1 and printing an error. Recursion explained. Let's explain how recursion really works using the concept of the call stack. Image calling factorial 3. The system keeps track of each function call in a memory. Factorial 3 calls factorial 2, calls factorial 1, calls factorial 0. Once factorial 0 returns 1, the stack starts to unwind. Factorial 1 returns 1 cross 1 equals to 1. Factorial 2 returns 2 cross 1 equals to 2. Factorial 3 returns 3 cross 2 equals to 6. We can imagine this as stacking plates. We can remove them from the top one by one. Recursion is not a magic, it's just a function like called find on top of each other. Want to practice? Try to writing a recursive function to sum all numbers from n down to 1. Benefits of recursion. So why use recursion? If loops can do the same thing, what is the benefit? Simplifies divide and conquer problems. Recursion naturally fits problems like medsolve or quicksolve. Cleaner code. Recursion can lead to elegant, minimalistic code that mirrors the mathematical definition of a problem. Self-similar structures. When a problem have repeating pattern or tree like branching recursion in a natural fit. Let's take the Fibonacci sequences. A recursive approach can define Fib, Fib n minus 1 plus Fib n minus 2, which is easy to read and implement. But there is a catch. Recursion is not always the best tool. We will cover it is a drawback next. Drawbacks of recursion. While recursion is elegant, it has a serious limitations that we must understand. Stack overflow. Each recursive call consumes stack memory. Too many calls can crash your program. Memory usage. Recursive solutions can use more memory than iterative ones. Inefficiency. Recursive solutions like Fibonacci without memorization repeat work, making them very slow. Debugging difficulty. Recursive functions can be hard to trace, especially when bugs are hid several levels deep. Resource intensive. Resource functions are often use more CPU cycles due to repeated function calls. One of the tips. Always ask yourself, is a recursion is the cleanest and most efficient an approach? If you not, consider an iterative solution is instituted. Summary of everything. Let's bring it all together with a quick summary. Function allows us to create a reusable modular pieces of code. Call by value means we pass a piece of data to functions safe and clean. Return values let functions send results back to the call code, and wait functions perform action but don't return data. Recursion solves problems by breaking them down and calling the same function and smaller version. A solid grasp of functions, the recursion sets the stage for higher level programming concepts like object oriented design, functional programming, data structure manipulation. Take a moment to reflect. Which of these concepts do you feel confident in? Which ones need more practice? Practice exercises. Now let's apply what we have learned with some hands-on challenges. Recursive Fibonacci function. Try writing Fibonacci n that return the nth Fibonacci number. Can you make it more efficient using memorization? Swap numbers using call by references. Use pointers in C to swap two integers. Practice tracing the memory changes. Create a void function that prints greetings in C, Python, or Java. Your choice. Try passing name as a parameter and personalize the greeting. I recommended doing this exercise on paper first, then trying them in code. Want a challenge? Combine all three into one program with a WinDrive interfaces. Function declaration and definition in C. Let's practice combining both declaration and definition in a C program code. What's happening here? The declaration tells the compiler what to expect the function name, parameters, and data type. The function provides the actual logic. This separation is common in larger C programs. We typically put declaration in header files and definition is implementation files. .c exercise. Ask learners to create .h file with a function declaration and link it with a .c file. .c file using the hash include directive. This reinforces modularity and clean coding practice. Call by value example in C. Let's reinforce the call by value concept with a familiar example. What does the value stay for? Because the function gets a copy of A, not the itself. Modification inside increment don't affect the original. Try it like add a return x statement and modified main to store the return value. That one way to apply the result even in a call by value. Ask in what scenario would call by value be per- preferred over reference call by reference example in C. Now compare that within this call by reference version. Void increment int x, open the bracket, x plus plus semicolon, close the bracket. Int main, open the bracket, int a equals to 5, increment a, print percentage d a, output is 6. This time we passed the memory address of allowing the function to directly modify its value. Notice we use cross x to access the value stored at a point. In main, we use an a to send the address. This is essential in C for swapping values, modifying large structures without copying. Dynamic memory management activity. Try writing a function with multiplies two integers pointers and update both values. Recursive factorial function in Python. We have seen factorial in C. Now let's look at this point. Def factorial n. If n equals to 0, return 1, else return n cross factorial n minus 1. Print factorial 4. Output is 24. The Python version is shorter and easier to read. Remember, Python use indentation instead of braces. No need to declare data types. Learners, what is the base case? What is the recursive case? The push further. Can you convert this into a loop? Or what happens if you input a negative number? Bonus activity. Add a print statement in the function to trace the recursion visual.